The second relaxation, the second thing that we want to think about now is that, well, what if there's some form of friction from either the air or the table? Or relax one of our previous assumptions. How do we deal with friction from the air or the table? And I say air here, but it really could be any medium, whatever the medium is that the spring is in. If it's in, say, a fluid, like brakes in a car, it could be a fluid with some viscosity. So we'll just say the medium, which is the fluid that the spring is moving in. So the main change here to Newton's law is that Newton's law is going to become the force of the spring plus the force of friction is going to be the net force, the new net force. And this is now what's going to be equal to the time derivative of momentum. And we've already detailed, given in detail what the force of the spring is, what the force of the spring could be in terms of displacement. So now we want to ask, what form does the force of friction vector take? And the answer to this is that it could take many forms. Just like for the spring force, where we only listed a couple, two possible forms, which is a linear function and a cubic function. The friction force, we typically assume takes the form of some function of the velocity vector which is the magnitude of the friction force times the unit vector that points in the opposite direction of the velocity vector. It has to point opposite to the velocity vector, just like the spring force has to point opposite to displacement of the spring. Now, there are many different types of drag laws or friction laws. Typically, in a fluid, you have two separate types of drag laws that are going to be valid for different conditions, different sized objects in different types of fluid flow. First thing that we see is that for very small objects in relatively nice flow, G is a linear function. And it's a linear function of the magnitude of the velocity vector. So G of V ends up being some constant A times the magnitude of the velocity vector, so that the force of friction ends up being A times the length of the velocity vector times negative V hat. Or V hat is the direction vector that points in the direction of the velocity. A note here, if friction is due to air resistance, this is a valid assumption for a low Reynolds number. Which is abbreviated as RE. And the Reynolds number is not non-dimensionless quantity, or non-dimensional or dimensionless quantity that essentially gives you an idea of how turbulent a given flow is a measurement of the ratio of the internal fluid forces to viscous forces within our fluid. This assumption was valid for a low Reynolds number. Alternatively, for higher Reynolds number flow, in larger objects which create more turbulence in the flow, maybe oddly shaped objects, Newton's drag law is a better assumption. And Newton's drag law is that G is quadratic. And V, or the G of the velocity, is some constant B times the magnitude of the velocity vector squared. So in this case, the force due to friction would be B times the length of the velocity vector squared times the direction this force is acting, which is always opposite to the velocity vector. And I want to note, just like before, that this is valid for a larger Reynolds number than Stokes' drag law. And just like before, also the drag law might be a complicated combination of Stokes, Newtons, and maybe a more complicated drag law as well. Just like the expressions for the spring stiffness from before. So let's look at a couple examples to kind of get an idea of what solutions are going to look like. And we'll just look at linear friction and linear Hooke's law, or linear spring law. And when you apply Newton's laws, you end up getting that the differential equation governing the motion of this spring will be m times the acceleration plus the constant a times the velocity, where a is the constant of proportionality for the friction, plus k times x is equal to 0. And this is a second order linear ordinary differential equation that you should be very familiar with from your first ODE's course, because this is the general second linear order constant coefficient when m, a, and k are constant. So it's the general type of equation, first, second order equation that you learn how to solve in a typical ODE's course. But so just like before, we can view this as a system. We define x dot as being equal to v, and then v dot, and we solve for v dot is x double dot, it's the same thing as v dot. This is going to be negative k over mx minus a over mv And so this second order ODE is equivalent to this autonomous system. Of linear first order ODEs. The equilibrium points of this system are when v is 0 and negative k over mx minus a over mv is equal to 0. And if v is 0, then this means that x has to be equal to 0 as well. So we have one equilibrium point. And this is where you might run into a little bit of a snag when you try to compute the exact solution in phase space. Because the differential equation in phase space for the orbits ends up becoming v dot over x dot dv dx is v dot over x dot, which is negative k over mx minus a over mv over v. And you can rewrite this as well as dv dx is equal to negative k over m x over v minus a over m. And this is non-separable. It's a non-separable, non-linear first-order ODE. It actually has a special name due to the Italian mathematician Cini. This is called Cini's ODE. And in this form, it actually is solvable. But it's kind of complicated. So I'm not going to go through and solve it. But it's possible to do. You'll hopefully remember how to solve this system of ODEs as well using what's called a characteristic polynomial to get the actual solution x of t. So you can go through and do this to actually directly solve for this problem. This is a homogeneous constant coefficient ODE whose solution is of the form e to the negative a over 2m times t times c1 e to the negative square root of a squared minus 4km times t plus c2 e to the square root of e squared minus 4km times t. And the solutions have different characteristics depending on the relative values of a, k, and m. If the a squared minus 4km is negative, and the solutions are decaying oscillatory functions, and you can actually re-express this solution form in terms of just a phase shifted sine function. And if this is greater than 0, then the solutions are just you have an exponential here and an exponential here. So you may have exponential decay or exponential growth depending on the relative values. But we'll consider the oscillatory decay because I think that gives the most interesting picture of the dynamics of this system. And this is for two different initial conditions for m equals 1, k equals 1, and a is equal to 0.5. You see initially the spring starts off and it moves back and forth, but as it moves back and forth, we have this decay. And in phase space, this looks very neat. We have the exact solution plotted out here along with the trajectory of a couple of different initial conditions. And what we're seeing here is that the equilibrium point that we calculated before is a stable equilibrium point, but it's not just stable, it's also asymptotically stable because the solutions as time goes to infinity are converging to this equilibrium point. And to get a better picture of this, we'll plot out the solution for more time t. So we're seeing that all solutions, no matter the initial condition, are converging to this point. And you might notice as well, so on kind of like the background of all these plots, I've plotted out the actual, the Nullclines, which are the curves that give the x derivative 0 and the y derivative 0. So for this case, the y prime equals 0 nullcline, or y dot equals 0 nullcline is when x is equal to 0, or v is equal to 0. Other way around, sorry, the x dot nullcline is when v is equal to 0, and the y dot nullcline is this line right here. This is when y dot is equal to 0. Or the function negative k over mx minus a over mv is 0. So at the intersection of the two nullclines, you get a critical point, and you can clearly see here that the slope here, or the y derivative here is 0, but if y derivative here is 0, and on any of these values on this line, the y derivative is 0. Same thing with this nullcline right here. And this is really neat, because this is giving us a picture showing the behavior of solutions. And in the background, I've also plotted the values of the individual derivative functions themselves, whether they're positive, dotted line means negative, solid line back here means positive. So you get an idea of how the solution is behaving in each one of these regions. Where the nullclines are separating, they're the regions. The next example we'll consider is linear friction in cubic spring force. And this gives us the differential equation mx dot dot plus a x dot plus k2 x cubed or k3 x cubed equals 0. And this differential equation is equivalent to the first order system of differential equations. X dot v dot is equal to v minus A over mv. So this is nonlinear second order. ODE, which is equivalent to an autonomous system. Of nonlinear first order ODEs. You go through and try and get the exact solution, you run into some issues here. You get a variation on Cheney's equation again, which is relatively hard to go through and solve. So I'm not going to go through and do this right now, but you can still apply our theory for the equilibrium points to find that there's going to be an equilibrium point when v equals 0 and negative k3 over m x cubed minus a over m times v is equal to 0. So when v is 0, that means that x has to be 0 as well. And we will be able to go through and apply some theory in a little while in the next couple lectures to actually classify the stability of these critical points. But I just want to give you an idea of what, how complicated the solution might end up looking. This is for m equals 1, k3 equals 0.5, a value of a equals 0.5. And you see here, we get a lot of kind of weird behavior where the velocity is kind of jumping around. You definitely have, for larger values of the initial condition, you have more oscillation here. But you still have a decay. It just looks quite different from the decay for the linear spring, which is to be expected. And if we look at the pictures of solution in the phase plane, you see very clearly this different behavior in the phase plane, where you do have decay. It's decay to this stable equilibrium point, which is actually asymptotically stable. But it's a much different from the previous picture in terms of how this is happening and how this is progressing. So you're still getting this decay, but you're getting it in a very nonlinear manner. This is just a picture showing very clearly that all these solutions are spiraling into this equilibrium point that we solved for before. Along with the Nullclines right here, and the Nullcline v equals 0, and the relative sign of each one of these functions. So the sign of the derivative. It's very, very neat. And just like you might expect, you get more and more complicated behavior in the phase plane, the more complicated you make the model. So for example, if you use quadratic friction, and cubic Hooke's law, or cubic spring law, the differential equation from Newton's law becomes this. Which is a second order nonlinear ODE. It's nonlinear in both the displacement and the velocity. Which can be expressed as the equivalent system x dot vita and this system is a system of first order nonlinear ODEs that's an autonomous system equivalent to the differential equation that's governing the motion of the system, just like all the other examples that we've considered. The solution curves to the system for two separate initial conditions that are differing in size. It look like this. So we still have this decay, but it's happening in much more complicated fashion here. But we can still go through and say that the equilibrium points are going to be when v is 0 and when negative b over mv squared minus k3 over mx cubed is equal to 0, which if v is 0 only gives us one equilibrium point again. And so the solution in the phase plane looks very, very complicated. But we still are seeing that this equilibrium point appears as if it's asymptotically stable, even though the solutions are spiraling into it in a very weird way. This equilibrium point appears like it's asymptotically stable from these numerical computations that we've kind of plotted out here. And the solution is, in fact, behaving exactly as we would expect it, based on the value of the function on the right-hand side of the ODE, which is very, very neat. And you can see very clearly that the behavior for an initial condition right here is much different than the behavior for an initial condition right here, which we're seeing in the solution profile when you look at the solution profile as a function of t. And so the last example that I'll show here, or the spring example with our air resistance, is going to be, if we take a fully nonlinear, so general spring force law and quadratic friction. And this results in ODE. This ODE right here, which is a nonlinear second order ODE, that is equivalent, just like the other examples that we've considered, to the autonomous system of first order ODEs it'll be negative b over m v squared minus k over m x minus k3 over m x cubed. And this is what solutions of such a system are going to look like in general for two different initial conditions. And for the phase plane diagram, when we look at the phase plane, we're again getting this, we can go through and get that there's going to be a critical point at 0, 0, 0, depending on if this is a hard spring or a soft spring. We'll get characteristically different results. But here I've just assumed this is a hard spring. And so this critical point ends up being an asymptotically stable critical point. However, it does take a little bit longer for the solution to go to this point. If you look at it for the numerical solution for larger intervals of time, this is what the phase plane looks like. So this is really neat, and the idea is that the examples that we've presented so far show that more realistic examples tend to produce nonlinear, more complicated ODEs that model a given physical scenario. And really, there's no end to how complicated you can make a model. For instance, for air resistance, you could choose, or the spring force for that matter. You could choose a Taylor series expansion to expand the force function, the force relationship, to any order that you want. Really, the only limit here is how much data you have and how realistic your data is that you're using to get your tension force relationship or your friction relationship. We can also combine these ideas with a lot of other ideas in physics as well. So what we're going to do is move into Lagrangian mechanics for the next part of the lecture.